Hey everybody, Jeff Oriema here. One of GraphQL's most useful properties for AI agents is that the API describes itself. An agent can inspect the schema and learn which fields and operations are available, can then use that information to construct a query. But what happens when the schema contains thousands of fields? Loading the whole thing into the model's context becomes expensive and less effective the more that you load. Before the agent can write an operation, it needs to locate the small portion of the schema relevant to the task. A recent article on GraphQL.org explores that problem through a purpose-built embedding model. The article is called A GraphQL Native Embedding Model for AI Agents, and it was written by Thore Koritzius. Thor and I met in Amsterdam at GraphQL Conf 2025, and I think his work is important in this new era of GraphQL and AI. This article shows why. Thor has produced concrete artifacts that the community can run, benchmark, criticize, and improve. We need that kind of work. We want the GraphQL and AI conversation to advance beyond broad claims about why the technologies should fit together. Thor opens the article with a serviceable description of the problem. Quote, "When you point an AI agent at a GraphQL API, the hard part isn't writing the query, it's finding the right fields." End quote. Modern language models are already reasonably capable of generating GraphQL syntax when they have the relevant schema in context. Production schemas introduce a retrieval problem. The agent may have thousands of field coordinates to choose from, many of which use the same vocabulary. For clarity, a field coordinate is how we describe how to find a certain part of the schema through its parent fields. A field named state, author, assignee, or created at might appear on dozens of types. If the user asks who is assigned to a support ticket, finding a field called assignee only gets the agent part of the way there. The useful coordinate is ticket.assignee rather than task.assignee or incident.assignee. The owner type carries essential meaning. Embedding models offer one way to search this information. In his article, Thor talks about how they convert text into numerical representations that can be compared for semantic similarity. You embed the user's question, compare it with an index of schema coordinates, and return the closest matches. General-purpose embedding models can perform that search, although GraphQL schemas are an unusual corpus. They contain compressed technical vocabulary, heavily repeated field names, type relationships, inconsistent descriptions, and organization-specific terms that may have little meaning outside a particular API. Thor's experiment starts with Qwen 3 embedding 0.6 billion parameters and fine-tunes it for mapping natural language questions to GraphQL field coordinates. The resulting model is open source and is small enough to run locally on many machines. That footprint makes the model practical in places where hosted embeddings API may be undesirable. The evaluation that Thor talks about uses 816 natural language questions across 5 production schemas: GitHub, GitLab, Linear, Shopify, and Singapore's Open Data API. None of those schemas appeared in the model's training data. The first metric is field recall. Recall at 20 asks how often the correct type.field coordinate appears somewhere among the first 20 results. The GraphQL fine-tune reaches 50.6% compared with 47.3% for OpenAI's text embedding 3 large. When the result set expands to 50 candidates, the fine-tuned model reaches 63.6%, while the OpenAI model reaches 59.8%. That is a meaningful improvement from a much smaller model running locally. The numbers also show how much work remains around the retrieval system. If the correct field is absent from the first 20 results in roughly half the questions, an agent will need additional strategies, such as re-ranking, iterative exploration, or using type relationships to narrow the search. The model addresses one stage of a larger process. After finding a promising field, the agent still has to determine how to reach it from a root operation, supply the right arguments, satisfy input types, and gather the other fields needed to answer the request. Summarizing further from the article, one example is that this makes the fine-tuning effect easier to see. The question is, when did I place this order? The candidate coordinates are order.created at, order.completed at, and order.updated at. The original Qwen model ranks order.completed@. first. After fine-tuning, order.created@ moves to the top because, quote, placed refers to when the order was created. Every candidate is a plausible timestamp, so the task depends on understanding the business meaning behind the field names. The article becomes especially interesting when it examines how schema fields are represented before embedding. Embedding the bare coordinate pull request.baseRefName produces relatively weak results. Adding its SDL context, or a one-line human-readable description, makes the field substantially easier to retrieve. On the GitHub benchmark, that change raises MRR from 0.39 to 0.72. MRR, for reference, stands for mean reciprocal rank. It measures how close the correct answer appears to the top of a ranked list, with higher scores rewarding systems that consistently place the right field near the beginning. A perfect score of 1 would mean the correct result always ranked first. The improvement from changing the corpus representation is enormous, and it combines with the benefit from fine-tuning the model. That result may have the broadest implications for GraphQL tooling. Introspection gives us a standardized description of an API, but raw introspection data does not automatically produce an effective retrieval corpus. Agents need a representation that preserves the context humans use when interpreting a schema. Directives could matter when they carry authorization or semantic information, and usage data might help prioritize the fields that real applications rely on most often. The right representation will also depend on the task. Answering a question about data may require a different index from choosing an action or constructing a complete mutation. Thore's benchmark gives the ecosystem a concrete place to begin evaluating these choices. It also raises the operational importance of schema descriptions. A clear explanation of the difference between created@ and completed@ helps developers today and may improve retrieval for agents tomorrow. So describe those fields, folks. Vague descriptions, overloaded terms, and company-specific abbreviations or jargon become easier to identify when they cause the wrong fields to rank. Now, there are plenty of open questions that Thore points out. Many user requests correspond to several coordinates rather than one labeled field. And we have to account for things like authorization, field cost, argument semantics, and the behavior behind an operation. And that can all influence whether an agent should use what it finds. Those boundaries are part of what makes the prototype valuable. Thore has isolated a specific problem and handed us a summary and an open model to jump off from. GraphQL introspection already powers documentation and editors, validation, code generation, schema registries, and so forth. Agentic software adds schema retrieval to that lineage. The schema becomes source material for an index that connects natural language intent with the capabilities of an API. I suspect work like this will contribute to better embedding models, but its larger contribution may be helping us to define what an agent-readable GraphQL schema looks like. A lot depends on that. I'll put links to the article and the model in the description, and I'm curious how you would build the retrieval corpus. Which parts of the schema would you preserve, and what additional context would you add? Let us know in the comments. That's it for now. See you next time.